we are able to set up export objects for a number of different formats, including STEP or IGES solid models and TurboGrid curve files. The type of export will depend on what CAE analysis system we will be using. We select the CFD solver we want to use, in this case Siemens STAR-CCM+, and the STEP export that we have just created as the target case. Then we choose the solver settings. The target Y+ in the mesh, the turbulence model, the number of computational cores, and the convergence criteria. Then, we define the number of operating points we wish to run in this simulation set. For each operating point, we define the boundary conditions, which can be pressure or mass flow based, including the inlet flow angle, given by 3 cylindrical component values. Once we have this CAE integration object defined, we simply select Run on the object, and the CFD analysis at all the defined operating points will go ahead. TURBOdesign1 automatically handles all the meshing, pre-processing, solver monitoring, and post-processing. Once the analysis is completed, the results are automatically returned to the TURBOdesign1 project manager, giving us our baseline characteristic. We are now ready to run a multi-objective, multi-point optimization on this case. We are going to use the reactive response surface with CAE to exploit the machine learning algorithm using a small but high-fidelity dataset. First, we define the optimizer input parameters: blade loading at the leading edge and the slope of the blade loading distribution, the 4 meridional geometry parameters, the wrap angle at the trailing edge, and a number of blades. TURBOdesign1 can estimate the ranges of the input parameters via the feature estimate input ranges on the optimization object. By using this feature, the software automatically employs a machine learning algorithm to calculate appropriate lower and upper bounds on the design space. We define constraints for the optimization, which will mark candidates that fall outside of these constraints as non-feasible. In this case, we constrain the maximum blade lean to no more than 40 degrees. This is to ensure a reasonable mechanical design that could be manufactured. Next, we define the objectives for the optimization. Because we are integrating multi-point CFD runs, into this study we can choose CFD results as objectives. We do not need to know about the intricacies of the 3D flow field or how it interacts with the rotor. We can simply ask for increased efficiency at each operating point and to maximize the value of minimum pressure. We do not care how the machine learning algorithm solves this task. We only care about the outcome. With 4 objectives, we will have a 4-dimensional solution space. Finally, we set the optimization meta-parameters. The initial DOE size, the number of response surface search iterations, and how many extra points to add after each iteration. We are now ready to run the optimization. As the study progresses, the design space is populated by the CFD runs, initially as a DOE, and then as a gradient search. After each iteration of 5 new candidates in CFD, the response surface is refitted, and the optimizer reassesses the route to the optimal solution using a multi-objective genetic algorithm on the surrogate model. You can see how the optimizer rapidly converges onto a solution whilst constructing the design matrix. After the iterations are completed, we can see the relationship between inputs and objectives, or between competing objectives. Each individual candidate in the design space can be selected for further analysis, either in TURBOdesign1 or go straight to further CFD analysis. Our selected candidates can then be compared against the baseline or any other candidate. In this case, we can choose 2 options: the peak efficiency performing design, which happens to have 14 blades, and the design which has the greatest cavitation margin, which has 16 blades.